In this video, we'll look at some function properties. Particularly, we're going to look at the exponential parent function y equals 2 to the power of x. So it's helpful if you're familiar with what this function looks like. Here's a sketch. I'll draw my x and y axis. It doesn't have to be perfect here, but you should put arrows in an x and y, and then show me that you know the function closes in on but never quite touches the x-axis and then starts to curve up really steep. That's a very rough sketch of the exponential parent function y equals 2 to the power of x. But from there we can get almost everything else we need. That is, for example, the domain. The domain is the set of x is an element of real numbers. Any x you want is allowed on this domain. You can be at negative 100, negative 1,000, and you'd still be validly on this function. Same thing, it keeps going right. It's going to go up steeply, but it's going to keep going for all x's. The y's are a little bit different story. The range is the set of y is such that the y's have to stay above that asymptote. Y is greater than 0. Other than that, y can be any element of real numbers. Intervals of increase. Those are the x's for which this function is getting bigger. We start at negative infinity, and slowly, very, very slowly, but still little by little bit, it's getting bigger and getting bigger. And in fact, its whole time, this parent exponential function is getting bigger. And we say the whole time by saying from negative infinity right up until positive infinity. X can be between any of those numbers. You could also say x an element of r, but I like to write it as an interval because sometimes there are limits. In this case, this function has no limits. It's increasing for all x's, which means where is it decreasing? None, or never, or na. Discontinuities and asymptotes. This function is continuous. However, it's worth noting, just as its property, that it has an asymptote, and that asymptote is y equals 0. How about zeros? Where does this function hit the x-axis? Answer, it doesn't. As we just said, it closes in on this asymptote. It never hits the x-axis. It always stays above 0. So for zeros, we would write none, or na. Where is its y-intercept? Hard to see with a rough sketch. That's why I said we got most of our properties, but to see the y-intercept, that's easy. And an important trick for the y-intercept, set x equal to 0 for this equation. And then you'll see an easy calculation. You just get y equals 2 to the power of 0, which is of course 1. So where's that y-intercept? Let's write it again here. Y-intercept is at when x equals 0, y equals 1. So now we know this hits right at a height of 1. Symmetry. For symmetry, we're talking really about two types of symmetry. Is it odd symmetry? That is, does it rotate around the origin 180 degrees with symmetry? Or is it even symmetry? Does it reflect in the y-axis, perfectly? I would watch the video on odd even symmetry if you're not sure what I meant, but in either case, it doesn't have any of those symmetries. It doesn't reflect in the y-axis perfectly. It doesn't rotate about the origin 180 degrees, so no symmetry. Let's talk about its end behaviors. First, we'll look at what happens when x goes to negative infinity, and as you go left forever, you get really, really small on y, but you never quite touch 0. So we say as x approaches negative infinity, y approaches 0. What happens as you get really, really big? That is, as x approaches infinity, the y is also going to get really, really big, so we say as x approaches infinity, y approaches infinity. Local maximum. This would be a turning point where there's a little peak, a little hill, and there aren't any on the exponential functions. It doesn't really have a local maximum. Now, local minimum is a bit tricky because clearly this function has some sort of lower bound. That is, it can't go below 0. It has to be greater than 0. But it would be, I think, not quite correct to say it has a local minimum because it never actually reaches a number. If we were to say what's its local minimum, what number would you give? Because you can't give 0. It doesn't actually touch 0. And any number you give, like 0.001, it goes a little bit below that. It goes, in fact, closer and closer. So there isn't really a good local minimum to say. However, it's worth noticing that, again, even though there's no local minimum, it does have a boundary. But that boundary is not a minimum, it's an asymptote. And that asymptote is y equals 0. How about absolute maximum? Does it have any local maximums? No, then it can't have an absolute maximum. How come? It goes up forever. And there's no, even if there was a local maximum, it goes up forever. It's a non-issue. How about absolute minimum? Again, same issue as before. It goes down forever, and so clearly it bottoms out, but we can't really ascribe a number to it. We can't say its minimum is this number. So you could say here, you could write a note saying stays above 0, but does it actually have a number that is its final number that it can't go below? No, because it keeps getting infinitely close to 0. So we'll say no absolute minimum. But you could say stays above y equals 0. And that just tells the reader, look, you know it doesn't have an absolute number that's its final checkout point, but it never goes below 0. Okay, where is this function concave up? That's where it's like a happy face. Or another way, if you don't like that analogy, it's where is the slope increasing? Well, this function, the slope, even though at the beginning it's increasing very slowly, it's still increasing. In fact, it's increasing the whole time. So where is this function concave up? Wherever the slope is increasing, which is for all x, or from negative infinity is less than x is less than infinity. Where is this function concave down? That would be where the slope is decreasing. Well, we just said it doesn't do that, so it's none, or NA. The function is never concave down when you're talking about this parent exponential function. And to that point, where are the points of inflection? There are none. If there was a change in concavity, there would be, but there isn't. So those are some of the function properties of the exponential parent function y equals 2 to the power of x.